In this lesson, we're going to look at horizontal and vertical translations of parent functions that we talked about in our last lesson. And to do that, we're going to start off with the parabola, y equals x squared, and we're going to horizontally and vertically translate that first. So if you haven't done so already, please put the following graphs into Desmos and to graph them right over here. Once you have that graph, your three parabolas should look something like that. We're going to quickly put some labels on it. We know this parabola in the middle, that's just our original function, y equals x squared, so that's our parent function that we'll be working with. We know that when you added 3 to the function, what it actually did was shifted it up 3 units. So we got this function up here, so we're just going to label it y equals x squared plus 3. And then when you graph this last guy, where we're taking the original function y equals x squared and subtracting it by 4, that actually shifts the parabola down 4 units, and we're left with this parabola down here, y equals x squared minus 4. So pretty simple. You're familiar with vertical translations from grade 10. When we're starting off with a function, we're going to extend it we're going to send it from quadratic functions to all the functions that we talked about in our last lesson. But when we add any numbers outside of that function, it's going to shift it up, just like it did here. And when we subtract numbers outside of the function, it's going to shift it down, just like it did here. So when talking about vertical translations, we're going to use the letter C. You might have used previously the letter K. It really all means the exact same thing. We're going to use K to represent a different transformation. So very quickly, we've got to update this because there's a little mistake. Let's cross out this K and we're going to use C and this K as well. And we're going to use C. So just cross that out so it's not confusing. So we already came to the conclusion in the previous example that when we add a number to a function, so when that means that C is greater than 0, then we're going to shift the parabola C units up. And when we're subtracting a value from the function or adding a negative value, so therefore C is less than 0, then it's going to shift the parabola down. So now we're just going to apply this to all functions. So it doesn't matter what the function is, it's going to hold the exact same property we just talked about. So we've written this now in function notation. So f of x represents any function you want. If we take any function and we add or subtract a number outside of that function, it's going to shift it up and down just like the parabola. So in general, when c is greater than 0, it's going to shift the function up. And when c is less than 0, it's going to shift the function that many units down. Let's take a look at horizontal translations now. So if you haven't done so already, plot these 3 functions into Desmos and then quickly sketch them on the graph here. So your 3 parabolas should look something like this, and let's quickly label them. We know what our parent graph is, y equals x squared will look like this graph in the middle. And then when you graphed this guy, y equals x plus 3 all squared, you might have remembered from grade 10 that something funny happens where when we add 3 to this x variable, you'd think we go right, but we're actually going to shift the parabola 3 units to the left. So this blue parabola over here is actually our y equals x plus 3 all squared parabola. And the same funny thing happens when we graph y equals x minus 4 all squared. It's actually going to shift the parabola to the right 4. So it looks like this. Y equals x minus 4 all squared. So everything's sort of backwards. And the reason why it's backwards is we're writing each of these equations in terms of y and not x, but we're affecting the x coordinate. So to understand what's going on, we really got to rewrite these equations in terms of x rather than y. So I'm just rewrote f of x as y. So we're starting off with our original equation y equals x squared. If I were to rewrite this equation in terms of x, it would look like this. X is equal to the square root of y, and we're going to put a little plus or minus in front of it. So this is the parent graph, y equals x squared, just rewritten in a different way, just written in terms of x. So now I'm going to move all of the x coordinates to the left, just like we did for this blue parabola. What I'm going to do is I'm going to subtract 3 from every single x coordinate. So it's going to look like this. Now that we have our x coordinate isolated for us, we have x is equal to plus or minus the square root of y. And if I want to move it left, I'm going to subtract 3. And that's going to take every x coordinate and move it to the left 3. And we're going to get this blue guy right here. But the reason why it looks like plus 3 is because, well, we got to rewrite it in terms of y. So the first thing I'm going to do is I'm going to move that minus 3 over to the other side, and we're going to get x plus 3 is equal to plus or minus the square root of y. That's where the plus 3 comes from. Now let's keep isolating for y and get rid of that square root. So we're going to square both sides, and I'm going to rearrange it. I know that plus or minus square root of y all squared is just going to be y. And I have y is equal to x plus 3 all squared. So even though I'm adding 3 to x, I know that that's just how it looks, and that's not what actually happened. What actually happened when I isolated for x is I subtracted 3, which is why it's going to the left. But when I rewrite it in terms of y, it looks like plus 3. So the same thing happened for this example here. It looks like a minus 4, but actually when the equation was in terms of x, we added 4 to it, and when we rearranged it, it looks like minus 4. So that's why everything's happening in what we think is a backwards way. So let's take a quick look at how we're going to represent horizontal translations algebraically. So for vertical translations, we use the letter C. For horizontal translations, we use the letter D. Don't be confused if it's a different letter than you used before. It really all means the same thing. If we're adding or subtracting that value directly to the x, we know it's going to be a horizontal shift. Remember that when we were dealing with vertical shifts, it was outside the function. It looked like that. So that's how we're going to tell the difference. So now what's beside this D is a negative value, and there's a reason why there's a negative value. So before I explain why there's a negative value, let's rewrite all of these equations from the previous example so that there is a negative value beside the D. So we're really going to be factoring in a negative one. So in this equation, I'm going to rewrite this. Instead of x plus 3, I'm going to do x minus negative 3. And in the next example, instead of writing x minus 4, I'm going to say x minus positive 4. So in both of these equations, I haven't changed the value of anything. Subtracting negative 3 is the same thing as adding 3, and subtracting positive 4 is the same thing as subtracting 4. So I haven't changed anything. But by taking out a negative 1 in both of these examples, what we're left with is the value of D. So I'm going to underline it. This is our value of D. So C was easier to see, but D, we got to factor out a negative 1. And the reason why we're doing all of this is by factoring out that negative 1, we have what was actually happening to that x coordinate. So it looks like the x coordinate was, all x coordinates were being added by 3, but actually they were being subtracted by 3. So this problem was moving to the left 3. And in this case, the parabola, every single x coordinate, 4 was added to it, which means we're going to the right 4. It looks like it was subtracted, but it was actually adding. So by factoring out a negative 1, we'd find the true value of D and what was actually happening to the x coordinate. So to continue with this summary, when D, and D is represented by whatever is beside this negative value here, when D is positive, like here, we're going to the right. So every x value is moved to the right, whatever D is. And when it's negative, just like here, every D value is going to be moved to the left. And I just noticed we're going to rewrite these two H's, little typo, we're going to put D in here. D and D. So let's summarize this for all functions now. So now we have function notation, not just for parabolas, but any parent function we want to start with. When our value of D, which is represented by whatever is beside this negative 1 here, when D is greater than 0, it's going to shift the function to the right. And when D is less than 0, it's going to shift the function to the left. If all of this is extremely confusing to you and you want to remember it in a completely different way, that is also fine. So some students like to remember that when D looks positive, we're actually going left, and when D looks negative, we're actually going to the right. Whatever works for you is just fine. So just as a quick reminder, how we tell the difference between C and D. So remember, this is our vertical and this is our horizontal. Is that if the value is inside where the x is, so directly touching the x, that means that it was added or subtracted to the x coordinate. And if it's outside of the function, it means it was added or subtracted to the y coordinate. So let's take a look at example number 1 and test your understanding. So in all of these examples, we are going to just list out the steps that we are going to take to graph each of these. So we have this function y equals square root of x minus 2. So first I like to pick out what is the parent function. So we have a giant clue to what the parent function is because we know we see a square root sign. So you can probably see that the parent function is the square root function. So that's what we're going to write. So we'll start by graph the parent, and that is f at x, or y, is equal to the square root of x. Okay, sometimes we won't be graphing the parent, sometimes we'll just be listing the coordinates, and that's fine too. So now the next step is we got to figure out what this -2 is. So I just quickly rewrote where C and D are in function notation. Remember, D, our horizontal, would be right in beside the x, and C is outside the function. So if this -2, if this square root were to extend and that -2 would be inside, then it would be affecting the horizontal coordinate, which is the x coordinate. But since it is outside of the square root, so it's outside of the function itself, it is our C value, so it's affecting the y coordinates. So go back to your rules for C. If C is negative, we know that it's going to shift the parent function 2 units down. So that's what we're going to write. So we're going to shift every point 2 units down. And our C value we know is -2. Let's try for the next example. So first, let's start off by figuring out what the parent function is. We've only looked at 6 of them. This one has a fraction and our x values at the bottom, so you can probably recognize that this is the reciprocal function. So we're going to graph our parent, which is f at x is equal to 1 over x. And again, sometimes we'll just be listing the points, we won't be graphing them. So now we've got to figure out what these two values are. We have a 3 and we have an 8. So maybe it might be obvious to you that this 8 is outside of the function itself, therefore it must be our C value. So I'm going to write a little C here. And this 3 is in right beside the x. It's within the function itself and it's right beside x. So this must be our D value. So if we go back into the rules for C and D, let's start with the hard one. Let's look at D. The actual value of D is -3 because we're going to factor out that -1. So because it's negative, we're actually moving to the left. So the graph is going to be shifted to the left 3 units. And our D value is equal to -3. And if we take a look at the rules for C, our C value is +8, which means it's going to be shifted up 8 units because our C value is +8. And let's take a look at our last example. Let's figure out what the heck this parent function is. We see these two absolute value signs, so we know the parent graph must be the absolute value function. So graph the parent, which is f at x is equal to the absolute value of x. And now we've got to figure out what is this 5 and what is this 1. It looks very similar to the quadratic function because for a quadratic function we just have brackets here and a squared. So you might be able to very easily recognize that this is touching directly the x. It's inside the function, so it must be our D value. and this -1 is outside the function, outside of the absolute value sign, so it must be our C value. So go ahead, stop the video, try to predict where this absolute value function is going, and then come back and check your answers. So if you're checking back in with your answers now, you should get there's a horizontal shift right 5, and our D value is 5. And there's going to be a vertical shift down 1, and our C value is -1. So now we're going to try a couple examples where we're actually going to graph these things. So there's a few different methods and strategies that we can use to actually graph transformations. So I'm going to show you a couple different ones. So for the first 2 examples, we're going to do it one way, and the second example, we're going to do it another way. So we're asked to graph this function using transformations. So just like we did on the previous page where we were just listing out our steps, we got to follow these steps now. So first we got to figure out what is the original parent function, and that parent function is the cubic function. So I'm just going to add that as a note to ourselves that the parent function is y equals x cubed, or f of x equals x cubed. I just don't have the room. And now let's figure out let's plan before we draw. We're going to plan out what these transformations are actually going to be. So you have to ask yourself, is this D or is this C? Well, take a look and remember D is right beside, inside the function, right beside the x. So therefore this must be our D value. So that has to affect the horizontal. So it's going to be a horizontal shift. In this case, I'm just going to use sort of short forms here. So I'm going to do H shifts, so horizontal shift. Our D value is actually -2. So we're going to the left 2. Our D is equal to -2, just as a reminder. So that's our sort of to-do list. First, we have to draw out our parent. Second, we're going to move every single point left 2, and then we're going to be done. So super quickly, this is why we practiced this in the previous lesson. We are going to draw out our points of y equals x cubed. So we know that the function goes through the origin, so 0, 0. We know it goes through 1, 1, -1, -1, and then 2, 8, and -2 and 8. However, we don't really have the room for that, so we're just going to keep going with this. Okay, so I'm just going to connect it. I know what the graph looks like. It looks something like that. Okay, so we're going to label the graphs at the end, but for now I'm going to do what is next on my to-do list, which is shift everything to the left 2. So I'm going to, okay, let's do it in red. So I'm going to take the origin, shift it to the left 2, this point left 2, and this next point left 2. And we're going to connect these dots. And here is our final graph. So I'm going to label it very quickly. This was f of x equals x cubed. And this here was our final graph of f of x is equal to x plus 2 all cubed. So if you couldn't see it, we're just moving every single point left 2, left 2, left 2, and connecting them. So when we transform, we try to have 5 points. In this case, our graph didn't allow it, so 3 is perfectly fine. So very quickly, let's list out the domain and range. So we know that the domain of all cubic functions are going to be that x is an element of R. And the same for the range. We know that the range is going to be that y is an element of R. So now let's take a look at this next example, and we're going to graph it in the exact same way we did the previous one. So let's first start off with what is the parent function. We see these 2 absolute value signs, so we know that the parent function must be the absolute value function. So we have y equals absolute value of x, or f of x equals absolute value of x. And now we've got to figure out what is this 2 and what is this 4. If we take a look and remind ourselves, what does D look like and what does C look like? We know that this guy is our D, it's inside the function right beside the x, and this guy is our C. So what I would suggest is to list out your steps now, graph it yourself, and then go back and check your answer against my solution. So if you feel comfortable, pause the video, try it on your own, and then come back to check. So if you've written out your transformations should be that we're going to the right 2 because our D value is 2, and we're going down 4 and because our C value is -4. We've drawn out the original parent graph of f at x equals absolute value of x, and now we're ready to start shifting. So what I like to do is, for translations, I like to do them together. So I'm going to go right 2 and down 4 all together. So for example, when I move the origin, I'm going to go right 2 and then down 1, 2, 3, 4 all together. So instead of doing 2 more separate graphs. So here's what I mean. So when we move the origin, it's going to go down here. When I move every other point, it's going to align this way, and every other point is going to align this way. And when we connect them, it's going to look something like this. So again, I just very quickly moved every single point, right 2, down 4, right 2, down 4, etc., etc. Let's quickly label our graphs. So this is our original parent, f at x equals absolute value of x, and here was our translated graph of f at x is equal to the absolute value of x minus 2, all subtracted by 4. When we take a look at the domain and range for this translated function, we can see that x can take on every single value. So we are going to say that x is an element of R. Taking a look at y now, we know that for an absolute value function, y is going to be restricted. Usually it's y has to be greater than 0, but in this case now, y has to be greater than -4. So we are going to say that y is an element of R such that y has to be greater than or equal to -4. So now we're going to take a look at the last 2 examples. So for these last 2 examples, I'm going to graph it in a different way. So we're going to start it off in the same way, though we have to figure out what is the parent graph here. Clearly it's the square root of x, and what are these 2 numbers going to do? So very quickly, we're going to write out that the parent graph is y equals the square root of x. And then we've got to take a look at these 2 guys. We have this 4 and the 3. Taking a look at D and C, we know that 4 is our D and -3 is our C. So if I were to write this out, our transformations would be a horizontal shift when we're going right 4 and a vertical shift down 3. So instead of working this out on a graph, instead I want you to think about this in terms of where each of the coordinates going without actually graphing them. So I like to sort of keep track by making a t-table, and on the left I have what's happening to our x coordinates, and on the right I have what's happening to our y coordinates. So our x and y, I'm just going to sort of make it thicker here. So we have x and then we have y. These represent our original coordinates of our parent function. So in this case our parent function is the square root of x. So now take a look at this 4. I know that means we're shifting it right 4. So ask yourself, is that going to affect the x coordinates or the y coordinates? Well, if we're going right, that means we're moving along the x-axis, which means it's going to affect the x coordinates. But what's happening to those x coordinates? Well, if they're moving right, that means we are adding 4 to them. And now take a look at our 3, this 3. We know that it affects the vertical shift, and it's shifting them down 3. So vertical means y values, and every single y value is going to be shifted down 3. So we have this new formula. We have all of our x values, we're going to add 4 to them, and all of our y values, we're going to subtract them by 3. So instead of graphing the parent and then shifting it, what we're going to do instead is list out the points of the parent and then list out the points of the transform function by adding 4 to the x's and subtracting 3 to the y's. So this may seem a little silly to do with translations, horizontal and vertical translations, but it's going to help us a lot when we go into more complex transformations like stretches and compressions. So we're just going to fill this in together. So our parent function we know is y equals the square root of x. And we're going to very quickly list some key points. We want to aim for at least 5. So we know the point 0, 0 is on here, the point 1, 1 is on here. When I put in a 4 under the square root, I get a 2. When I put a 9 under the square root, I get a 3, and that's enough. I know I just said 5, but we're going to stick with 4. Okay, so all of these points are going to get transformed. So we're just going to do arrows here, and they're going to get transformed based on the equations that we've sort of created here. So every x value is going to increase by 4, and every y value is going to decrease by 3. So let's do all the x values first. So our new x values, maybe I'll do them in blue. So our new x value is going to be 0 plus 4, which is going to be 4. Our new x value here is going to be 1 plus 4, which is 5. We have 4 plus 4, which is 8, and then 9 plus 4, which is 13. And now let's do our new y values. So our y values are all going to be subtracted by 3. So 0 now is going to become negative 3, 1 is going to become negative 2, and etc. So instead of 0, we're going to have negative 3. Instead of 1, we're going to have negative 2. Instead of 2, we have negative 1. Instead of 3, we're going to have 0. So now these are our new points for our function, and we're ready to graph it right away. So now let's go ahead and graph. So we are graphing these points directly. So we've already taken into account the parent function and its transformations. So now if we're ready to graph, I noticed taking a look at my x values, I'm not going to really make it on here because I can get to 4 and 5, but not 8 and 13. My y values are fine. So let's actually change the scale. Let's actually go by 2. So let's make this 2, 4, 6, 8, etc., etc. So we'll sort of get the idea. Mine's messy because it's on the iPad. You guys can make yours a little bit neater. Okay, we'll keep the y scale exactly how it is, so just go it by ones. And now let's quickly graph this. So if we have 4, negative 3, negative 1, 2, 3, it's going to look something like that. Let's change that to blue. There we go. And we have 5, negative 2 is going to look something like that. 8, negative 1 is going to look like that. And we won't make it to 13, and that's okay. So let's connect these two. We know that it's going to look something like this, and I'm going to continue. And there we have the completed graph of the transform function. So this was a different way to do it, just sort of algebraically or just manipulating the points and not graphing more than one graph. Let's finish off this question by filling out the domain and range. So if we take a look here, the domain only exists after 4 and above. So we are going to say that x is an element of R such that x has to be greater than or equal to 4. That's the minimum. And taking a look for y now, y only exists above negative 3. So we are going to write that y is an element of R such that y is greater than or equal to negative 3. So now we're ready to work on our last example. Y equals 1 over x minus 2, all added by 1. And we're going to try to graph it in the same way that we did above. Even though it seems like it's harder, it's going to make our life easier later on to know both of these methods. So what I suggest is list out the parent graph, list out the transformations, and then come back to the video and check your answers. Okay, so if you've got your transformations right, we know that the parent graph is the reciprocal function, f at x equals 1 over x. We know that there should be a shift, a horizontal shift right 2, because our d value is positive 2, and a vertical shift up 1, and that's because our c value is positive 1. So now let's go ahead and make our sort of key. What are we going to do the x coordinates, and what are we going to do the y coordinates? So that's what we're going to do here. So let's take a look at this guy. Horizontal shift right 2. We know it's going to affect the x coordinates. And because we're going to the right, we are going to add 2 to all the x's. And now let's take a look at our vertical shift. Vertical means we're affecting y, and we're shifting it up 1, which means that we're going to add 1 to all the y values. So now go ahead and fill out your t-chart if that's how you chose to organize yourself, and list out the most important points of the parent graph. Usually for reciprocal function we use 6, 3 on one arm and 3 on the other, and then list out where they're going to be transformed based on our sort of cheat sheet we've created over here, and then check back in the video and make sure that your answers are accurate. So I've just set up everything right before transforming. I've written down the 6 6 crucial points for the reciprocal function. I've chosen 3 on the negative arm and 3 on the positive arm. You could use whatever points that you like. These are just nice and easy to remember. And now we're going to use our sort of cheat sheet to transform these points. Okay, so we are going to take -2 and add it by 2. We're going to take our -1, also add it by 2. We're going to take all of these x coordinates and add 2 to it. So here are our new x coordinates. Check to make sure you have the same thing. Now we're going to work on the y coordinates. We're going to add 1 to every single y coordinate. So all of these coordinates here, we're going to add 1 to them. And here are our final coordinates. So if you started with different points, they'll have different coordinates, but it should still all be on the same function. So now we're ready to graph these coordinates here. So I took a quick look at my scale and I can fit everything on the graph, so we're ready to plot. So we're going to start with the first point and plot downwards. Okay, so we have the point 0 and 0.5, which will be about here. 1 and 0, 1.5 and -1. And now we have 2.5 and 3, 1, 2, 3, 3 and 2, and 4, 1, 2, 3, 4, and up 1.5. So we can sort of see our 2 arms. We have 1 arm here, and we have 1 arm here. What's important is we also figure out where the asymptotes are. So remember what our original transformations were. We were moving to the right 2, and we're going up 1. So what that means is our asymptotes also go along with that. So originally we had an asymptote here along the y-axis here at x equals 0. Well, when that gets moved to the right 2, it's going to end up over here to the right 2. So I'm going to draw a dotted line down where this asymptote is going to be. Let me make that a bit thicker so you can see it. Okay, so we have a new asymptote down here at the line x is equal to 2. Now take a look at our other asymptote. Our other asymptote used to be along the x-axis at y equals 0, but everything got moved up 1, including that asymptote. So now the asymptote is going to exist here at y equals 1. So we're going to go ahead and write and put a dotted line to represent that as well. So we have our new asymptote here at y is equal to 1. And now that perfectly goes with our points, and now we can comfortably connect these because we have a better idea of what it looks like. We know that will continue on forever, so we're going to add in our arrows. And here's our final graph. So now let's finish this off by figuring out the domain and range. Remember, for these reciprocal functions, the domain and range can be absolutely everything except for one single value. So for the x, that single value is 2. So we are going to say that x is an element of R such that it cannot equal 2. That's the only restriction. And for y, our restriction is that y can be absolutely anything except it cannot equal 1. That's the only value it cannot take on. So y is an element of R such that y cannot equal 1.